Assalamu alaikum everyone. My name is Amri Shamim, student of Department of CSE, Kumila University. Today I will be presenting a core topic in our digital image processing, that is Fourier transform and frequency domain processing. I will explore how looking at image through the lens of frequency allows us to perform advanced operations that are difficult to achieve in the spatial domain. Uh, our discussion today is structured into 10 main sections, covering everything from the fundamentals of Fourier transform to the workflow of 2D and TFT, and both smoothing and sharpening filters like IDL, Bandwidth, and Gaussian models. Uh, mm, since we have a quite large number of topics to cover today, I will try to keep my explanation precise and straight to the point so that we can grab the core concept effectively. Let's start our presentation. In introduction part, let's discuss about in digital image processing. We typically think of the spatial domain, where the manipulate pixels based on their coordinates x, y. However, the frequency domain offers a different perspective. It allows us to analyze the rate at which pixels instantly change. High frequency represents sharp details and edges, while low frequencies represent the smooth, consistent areas of an image. This analysis is vital for tasks like noise removal and feature extraction. The Fourier transformation is a mathematical tool decompose a signal, in our cases an image, into its constituent sine and cosine waves. Essentially, it tells us how much of each frequency is represented in our image. By transforming an image, we can see patterns that are visible in the standard pixel view. Frequency domain analysis. To visualize this, think of smooth background or large object as low frequency components. They change slowly across space. Conversely, high frequency components are the rapid changes, the edge, and the fine textures, and unfortunately the noise. The center of a Fourier spectrum, known as the DC component, represents the average intensity of the entire image. The Fourier transformation equation. Mathematically, the 1D Fourier transformation of a continuous function f of t is defined by the integral shown here. We can see the slide where multiply our function by a complex exponential and integrated over all time. This transform our time domain is signal into a frequency domain representation. 2D discrete Fourier transformation. Since digital images consist of discrete pixels, so we use the discrete Fourier transformation for an image of size m into n. The 2D DFT maps spatial pixels f of x, y to frequency coefficients of f of u, v. This formula is the engine behind almost all frequency domain processing in modern computing. Inverse DFD, after we have processed our image in a frequency domain, we must bring it back to the spatial domain to see the result. The inverse DFD allows for these reconstructions. Now, notice the formula is nearly identical to the forward transfer, but the positive exponent and the normalization factor of 1 over m into n. Digital processing workflow. The workflow flows a logical sequence. We start with our input image and compute DFD. We then apply a filter h of u, b. This filter spectrum is the transfer back by the inverse DFT to produce our final processed output images. And the filtering process. The main advantage of filtering process in the frequency domain is simplicity. In the spiral domain, filtering requires complex convolution. In the frequency domain, this is replaced by simple point-wise multiplication. We simply multiply the image spectrum by filter transfer function to filtering the process. Here is the equation we are seeing that mathematical properties. Several properties make this domain powerful. Linearity allows us to process components independently. A rotation is fascinating. If you rotate an image, its frequency spectrum rotates by the same angle. Most importantly, the convolution property proves that multiplication in a frequency domain is equivalent to convolution in the spiral domain. Frequency domain filters overview. Filters are generally categorized into four types: low pass for smooth and high pass for sharpening, and band pass reject for isolating or removal specific frequency ranges. This table summarize how each affects the final image. We can see there filter type and action and its application. Smoothing filters. Let's focus on the smoothing. By attenuating high frequency components, we reduce sharp transitions. This result in image blurring and is highly effective for removing salt and pepper noise or preparing an image for high level object detection. An ideal flow pass filter ILFPF. The ideal low pass filter is the most basic. It cuts off all frequencies outside of a specified radius. While mathematically simple, it has a major drawback. It causes a raining effect, creating ghostly ripples around the edges of object in an images. The Butterworth filter provides a smoother transition than the ideal filter by adjusting the order, and we can control the slope of the cutoff in lower orders, and the raining effects is significantly reduces, making it much more useful for practical applications. Um, and next topic is the Gaussian filter is the gold standard for smoothing because it transfer function is a Gaussian curve. It provides zero ringing effect. It results in the most natural looking blur and is widely used in professional image editing software. Low pass filter comparison. Comparing the three, the ideal filter is too harsh and causes artifacts. The Butterworth is the flexible middle ground. The Gaussian is the smoothest and the most artifact free, making it the preferred choice for high quality smoothing. Sharpening filter, high pass. So now we move to sharpening. Sharpening is the inverse of a smoothing. We block the low frequencies and highlights high frequencies. This emphasizes edges and final details, making image appear much crisper. Ideal high pass filter. The ideal high pass filter blocks all frequency inside a circle of radius. Uh, like its low pass counterpart, it is prone to ringing artifacts and often produces a very harsh looking edge enhancement. Butterworth high pass filter offers a more Refined sharpening, it allows for a gradual transaction, preserving some of the low power frequencies context while still making the edges stand out clearly. A Gaussian high-pass filter provides the cleanest sharpening result. It enhances edges without adding artificial noise or ripples, providing a very smooth and professional-looking detail enhancement. In summary of sharpening, the ideal filter is often to distort it. The a butterwood is excellent for tunable sharpening. The Gaussian provides the most natural edge enhancement with the fewest artifacts. Uh, it's all today from its last topic. I had tried to precise and to conclude the topic very shortly. Uh, so thank you everyone for your attention. Bye bye.